Hello, my name is Colin Ngo, and I am from Section C of Physics 2211, and today I'll be going over the Lab 1 constant velocity. The purpose of this lab was to observe, analyze, and compare the motion of an object moving with constant velocity using a computational model, as well as observations and fundamental physics principles. So just quickly, our results preview here. We had findings that saw that the computational model yielded a linear prediction of motion, and our observed data saw a slight deviation from that prediction model due to some inherent errors such as friction, and we'll get into that a little bit later. And here we have the data yielding this graph that we see. We have our predicted data, which is from our computation model, as well as our observed data from the experiment. So this lab has three main components, which is our constant velocity, our main physics idea which we applied, which is the momentum principle, as well as the computation model that we coded using VPython. So we just want to start with Newton's second law here, which F net equals mass times acceleration. And from this, we use the momentum principle to derive a certain equation that we'll need later on. F net equals mass times acceleration, and from that we know that Newton's second law says that delta momentum is divided over the change in time, and we can multiply this change in time over to the other side, and this yields a change in momentum equals F net times delta t. And from that we get this equation, and knowing that momentum equals mass times velocity, we can just divide mass out, and this yields our velocity update formula. Now this is final velocity equals initial velocity plus F net divided by mass times delta t. And in this case, F net equals 0 because our forces are balanced. And so this ends up zeroing out, and we know that V initial is just equal to V final, so our velocity is constant. In addition to this, we have another formula, which is the position update formula, where R final equals R initial plus constant velocity, in this case, times delta t. So our lab setup, we had some initial conditions where our position vector was 0, 0, 0, and our initial velocity had some x component. Our materials were a metal cylinder, a meter stick, our table, and the camera that we used to record the experiment. Our system we defined was the metal cylinder, which is our object in motion, and its surrounding was basically everything else, which includes the earth, the table, the air, etc. Our assumptions were that friction and air resistance were negligible in this case, and our units were meters and seconds. Our axis orientation we defined as right positive and up positive as well. Here's a diagram of our lab setup where our metal cylinder is positioned right here, our meter stick is along here, and our table is what we use as a background where we recorded top down. And this is our experiment in video. So with the data we collected from our experiment, we graphed these two lines. Our computational model was used to graph this linear orange line, and then our observed data graphed this other blue line. And from here we see our comparison where the two lines are somewhat similar up until point 4, in which the observed data slightly deviates due to some errors that we'll get into later. Our computational model does predict with constant velocity, and we see somewhat similarities, but also some differences later on. So using our computational model, we have our initial conditions that we inputted, which is our position vector 0, 0, 0, and then our velocity vector, which was 0.3633 meters per second as our x component, and our y and z component were 0. Our start time was 0, and our time step was 0.02 seconds. We had a while loop used to update our position, and so we had a total time of 1.667 seconds. Our net force vector was 0, 0, 0 because our forces were balanced. And our velocity update equation is right here as well, and because F net equals 0, this has constant velocity. Our position update equation is here as well, that outputted these two graphs, in which position was linear and had a constant slope due to the horizontal line of velocity, which has a slope of 0, as you can see right here. So some sources of error that we saw were external forces and human error, where the external forces were friction and air resistance. And these two forces acted against the motion, which slowed it down slightly, and that was the reason for the deviation from the linear prediction model. And then our human errors were position tracking, which we used a tracker software to map the center of mass. However, just based on human error, we could have mapped that slightly off with some margin of error. So we want to answer what if the axes were flipped, and in this case, if they were interchanged, our slope for the two graphs would just yield as negative. And then we also want to answer what does it mean in terms of identifying the push and pull forces. So we have a free body diagram here that shows that normal force and force of gravity are equal and opposite, so F net would equal 0. Conclusion is that this lab showed that an object with 0 net force moves at a constant velocity, and the tracker data and computational model agreed closely, confirming the prediction of Newton's second law. However, we did see some slight deviation due to the friction and air resistance. Thank you.